Hey guys, welcome to video 9 of the thermodynamics series. In this video we're going to be focusing on two other processes from the different thermodynamic processes that we've begun looking at, and those two are named the isochoric process and the isobaric process. Now at the end of the last video I gave you a challenge to figure out, is there a thermodynamic process where the work that's done during the process could be equal to zero, whether through compression or expansion. So without further ado, let's get into it. So in short, the answer is yes. There is a thermodynamic process in which no work is done. So how did I come up with that answer? Well, if I think of the different ways that we've established that I can know or calculate whether work is done, they are the following. I could either say if pressure is constant, work is equal to pressure times a change in volume. I could also use an integral definition if you're in calculus, which is work is equal to integral P dV. But in both cases, volume is changing, whether pressure is constant or not constant. Finally, we looked at a way that you could do it graphically, which both of these ways sort of imply, specifically the calculus representation, and that would be to find the area underneath the function on the PV diagram. So all three ways are ways to calculate if work is done, and all three ways require that there be some change in volume. So if I take a look at a PV diagram, let's represent a PV diagram for each of these possible ways. The first way, where I would be using the P delta V equation, would only be possible when work is, or when pressure is constant. So that would be something that looks like this. This is showing a change in volume from point A to point B, but no change in pressure. This is a process that we call an isobaric process. So if you think of the term barometer, right, that is something that measures pressure, isobaric means that the pressure remains the same. So from point A to point B, there is a volume change, but there is no change in pressure. In this case where pressure is constant, I can use work is equal to P delta V to calculate work done in this case. Now we will get into that in a little bit more detail in a minute or two. The integral definition is one in which pressure is not constant. And we've already sort of established this, so I'm not going to get into too much detail, but it would be something where any combination of points or a state change from A to B where we have some sort of curve to the line, right? Or even some sort of linear line, which is just an approximation of the same state change. Either way, there's a change in pressure, and so I have to be able to calculate this in some way. Now the last way, finding the area under the graph, is what I would resort to if I was not able to integrate and I did not have the tools yet in order to do that. So I could calculate the area under this line and I would get a work value. Now the only time when work is not done, like we said before, is that when there's no change in volume. That means that nothing's moved and therefore there's no work done. So pause the video for a second and try to draw or sketch a PV diagram. So sketch a PV diagram in which you show that there is no work done as the state of the gas changes from one point to another. So hopefully you were able to draw a straight vertical line. This is the only way to have an initial point and a final point in which there is no change in volume. In other words, they have the same x value and two different y values. This is why I call this a PV diagram. Now we know if you were to do a function test, right, that this is not a function because there is no change. There's two variables for y, or two answers for y, for one input of x, which we know violates the definition of the function. And so in this case, we could say, as a reminder, this is a diagram. It's showing a change in the states. Now it is also a graph. So if I were to calculate this, it makes no sense, right? In terms of it being graphical, it's undefined. So if I were to draw the arrow from A to B, that would be saying that I had a drop in pressure and no change in volume. This would be a case where, if you look at it visually, there is no area under this function because there's no under this function, if you will. So in this case, this is a thermodynamic process where that is possible. There's a change from one state to the other. There's just no volume change. And this is a process that we call an isochoric process, sometimes also called isovolumetric. So an isochoric process is one in which the volume does not change. There are other changes going on in macro state, it's just that volume is not one of them. It is also a thermodynamic process in which no work is done. So my next question then is to review the sign conventions, which work is the most confusing of if you're still getting used to the convention of work done by or on the gas. Now remember, these are happening at the same time. And if you need a refresher, please go back to the last video and watch that. Otherwise, this will make no sense. So if I have an isobaric process and I show the arrow pointing to the right, we would call this an isobaric expansion. If I have the arrow pointing to the left, I would have an isobaric compression. Now, if I take an isobaric expansion, for example, what would the sign of the work be of the work done on the gas? And what would the sign of the work be at the same time for that expansion of the work done by the gas? Pause the video and try to figure those out for yourself. Hopefully you're able to see that according to the rules we made before that still hold true. If I have an expansion on the gas, then that would be a negative value. So we oftentimes would write for the isobaric process, work is equal to negative P delta V. This is implying that this is work done on the gas. Now, if you were writing work done by the gas for the exact same process, that would just be a positive value. So always be careful that when you're dealing with the first law of thermodynamics, that you read carefully to assess whether you're looking at work done on or by the gas. Most of the time, we're going to assume that the work is being done on the gas. That's the perspective we're going to look at. But it can change, so read carefully. Now, in an isobaric compression, pause again and try to write the sign for the work done on the gas and the work done by the gas. So in this case, the work done on the gas as it compresses, this would be positive, and the work done by the gas in the compression is negative. Either way, the sign convention still holds. Next, just to hit the point home, for an isochoric expansion and an isochoric compression, pause the video and write the sign of the work. Hopefully you were thinking, what the heck? There's no even reason to pause. First of all, there's no work done because I have no area under this function. Secondly, it doesn't even make sense to say expansion or compression because the volume is not changing. In other words, in both cases for isochoric process, whether the arrow is pointing up or down on this function, that is a zero amount of work done. Now there is still something going on here as we're going to look at, but there is no work being done, and that's important to remember. Next, let's take a look at what physically has to happen for an isobaric or an isochoric process to occur. What I'd like you to do first is consider the isobaric process. Remember, this is the process in which the volume changed, but the pressure stays the same. And we're going to look at this for an expansion and a compression. So the first thing I'd like you to do is pause the video and try to determine, is heat flowing into or out of the system for the expansion and also for the compression isobarically, and then determine, was there an increase or a decrease in internal energy, if any, for the expansion and the isobaric compression. So if I take the isobaric expansion first, the first thing that I'd like to do is determine what I would expect to happen if there's no other controls happening to the system. Well, if the volume increases, I would expect the pressure to drop. So if the pressure is staying the same, then that means that there has to be heat flowing into the system during the expansion. So Q would be positive for heat flowing into the system. Now, if we're looking at the work here being done on the gas, right? And so if that means that work is negative and Q is positive, let's see if we can figure out what delta U would have to be. So in order to know if delta U has increased, decreased, or remained the same, I would need to look at whether temperature has increased, decreased, or remained the same, because that's the sole influencer of the internal energy, delta U, or U. So if I increase the volume from state A to state B, and the pressure stays the same, as volume increases, if I look at my ideal gas law, the temperature should increase if everything else is held constant. And that is actually what I see, that there is this direct proportion between the volume and the temperature for this isobaric process. So if the temperature increased, then that must mean that U, or the internal energy, increased. So delta U would be positive. So if I take a look at my first law of thermodynamics statement, delta U equals work done on the system plus heat flowing into the system, I see that heat flowing into the system is positive, work done on the system during this expansion is negative, then delta U could be a variety of different things, but I've just said that it is positive in this case. So if I take a look at these signs here, right, in order for this answer to come out positive, and I have a negative value and a positive value, it means that the positive value would have to be greater than the negative value. Otherwise, the delta U would not come out to be positive. So if we think about what this means, is that during an expansion, I ended up having to put more heat into the system than I got in terms of the quantity of work done. So for this rightward pointing isobaric expansion, the heat that I put in exceeded the amount of work done, and therefore I have a positive change in internal energy. Next, let's look at the isobaric compression. So if you'd like to pause the video and correct or revisit your answer, go ahead and do that, or just keep watching. So if I isobarically compress this gas, what I would expect to happen on first analysis is that as the volume decreases, I would expect the pressure to increase. But if the pressure remains the same, that means that there is heat leaving the system. So heat leaving the system would mean that Q is negative. Now, if I'm thinking about the relationship that I just described between volume and temperature, as the volume decreases and the pressure stays the same, I would expect temperature to decrease, meaning delta U is also negative. So if Q is negative and delta U is negative, but I'm looking at work done on the gas during this compression is a positive value, then this means here that the amount of heat removed from the system was greater than the amount of work done during that process. And so the net change in internal energy was negative. Now this is a very important concept, and it's not 100% clear right now because we haven't looked at any of these processes in combination with one another, which we call cycles, thermodynamic cycles. We've just looked at individual processes. But if we think about what's happening here, the isobaric expansion says that more heat goes in than work is done, and the isobaric compression says more heat goes out than work was done, then this actually lays the foundation for some very important concept we're going to see in about 2 videos down the line. And that is the difference between a heat engine and a refrigerator. Because you may not have known this, but they're really the same thing acting in reverse. Now let's look at the signs for the first law of thermodynamics for an isochoric process. Now remember, we're neither dealing with an expansion nor a compression because there's no volume change. So in a sense, we're saying that this container is fixed in size. There can be no change in volume, but there might be a change in the pressure and the temperature. So if we look at the PV diagram, yes, there is a change in the pressure. So let's start with the arrow pointing down. If there's a drop in the pressure, that means that if the volume can't change, there also is a drop in the temperature due to the ideal gas law. There's no exchange of material with the environment for this first case, we're going to say that this container is fixed. It can't gain or lose any material. So if the pressure drops and the temperature drops and there's no work done, then that means that all of the heat that is in the system, or some of the heat that's in the system, I should say, is leaving the system. So there's a drop in the internal energy. So negative delta U would equal a negative Q. Now, if we point the arrow up, we would see that that indicates that there has been an increase in pressure. But remember, this is all happening almost instantaneously. So it's basically saying you have this fixed container with no particle exchange with the environment, and you all of a sudden increase the pressure, and that results in an increase in the temperature, which means that there would have to be heat flow into the system somehow, but not in the form of particle exchange. So there's heat flow into the system, and the internal energy is increased because there's a temperature increase. So for the arrow pointing down for the isochoric, I have a negative delta U because I have a negative Q, and for the arrow pointing up for the isochoric process, I have a positive delta U and a positive Q value. So at this point, it would be useful to take the chart that you hopefully started constructing from the last video with the following processes and expansion compression components listed. So we so far have an isothermal expansion, an isothermal compression, we have an isobaric expansion, an isobaric compression, and then we have an isochoric process, which is instantaneous and is neither a expansion nor compression. So I'm going to go ahead and put all the values of the signs 0, plus or minus in for each of these so far. So I'm going to leave you with a challenge as always. And in this challenge, I want you to try to figure out if I have a completely insulated or completely isolated container and I somehow achieve an expansion, what would have to happen if I have a negative work done on the gas, no heat exchange? What would happen to the internal energy of the system? Do that for an expansion and a compression, and then we'll come back in the next video and take a look at how we can piece all of these different thermodynamic processes, including this last one we're going to discuss, all together in order to make a cycle. In other words, a heat engine cycle or a refrigeration cycle.